All right, welcome back. And now what we're going to do is we're going to talk about another topic that is really important in calculus, and also that comes up later on in Calc 2, is this idea of linear approximations and differentials. So that's what we're going to start talking about today. So let's start with the idea of what is a linear approximation. Well, the easiest function to work with is a linear function. So when we say a linear approximation, or when we talk about, well, I'll just stick with linear approximations, but when we're talking about linear approximations, we're going to use a line, a straight line, to approximate a particular value. For example, if I have a curve, right, and I want to estimate a value, okay, on that curve, as long as I'm real close to this particular point on the curve, I could approximate it by using the tangent line to that point, and then estimate another point. Let's say I'm interested in another point. Well, I could use a linear approximation to kind of estimate what the value of the point would be on the curve, and as long as I'm within a certain closeness to the point, then I should be within a certain amount of accuracy. There'll always be error, but that's the idea behind linear approximations. I'm going to approximate a value of a curve by using the tangent line to that curve. Okay, so here's how it works. So remember, from before, we have f of x is equal to f of a, plus f prime of hold on, is that right? Yeah, f prime of a times x minus a. Okay, and remember, this was developed, this is the equation of a tangent line that was developed directly from the quotient, right, the derivative, right? And so, now, this we can replace with y. So now, this is the tangent line to the graph of the function at a. Okay, and this is the equation that we used. Okay, now, if I give an example, let's use f of x is equal to, f of x is equal to 1 over x, the reciprocal function. Okay? So let's say, okay, the reciprocal function looks like maybe this. I'll complete the graph here. Let's go here, okay? So there's the reciprocal function, okay? Now, let's say at a equals 2, right? So let's consider this function at a equal to 2, right? And so let's say okay. Now, so the equation, right, of the tangent line would then be given by y equals f of a, which would be 1/2, so this would be 1/2 plus the derivative, right, f prime of a. Okay, so what's f prime of a? What's the derivative of f? It's going to be negative 1 over x squared, right? So f prime of x equals negative 1 over x squared. So that means f prime of a is going to equal negative 1 over 2 squared, right? So let's do here 2, and this will be 2 squared, so it'll be negative 1/4, right? And so we get a negative 1/4 times x minus 2, right? And so of course we can write this as a subtraction. And so there's our equation for the tangent line, right? And we can write it that way. Okay. Now we can also write it in y equals mx plus b form like we have in the past, but let's leave it in this form. Okay, now, so here's the thing. Note that for any x value near 2, the graph of the tangent line is going to be close to the graph of the function. In this case, 1 over x. And as a result, we can use the equation of the tangent line to approximate f of x for any x value that's near 2. And again, the operative word is near. Okay, so we're going to have to explain what that means. Okay? So now, what if we use, in this example, what if we use 2.1? Okay, so let's do it. So now let's approximate f of 2.1. Right? So, before I do that, notice that the reason why is because, see, if we use the tangent line, then as long as we're close to 2, then we're going to be close, right, on the tangent line, we're going to be close to f of x, or excuse me, well, f of x if you want. Okay, so we can pick any x value in here, and on the tangent line we will be close to f of x within a certain degree of accuracy, right? And so to better see it, if we get really close, if we were able to project this out, right? If we were able to like zoom in, right? Then we might see something more pronounced and say, okay, well, we've got this curve that now looks like that, and the tangent line does that, and so now you're really close, right? It seems like it's really close, right? Because remember, the more you zoom in on a curve, the straighter that it looks, right? So that's the idea behind linear approximation. It is, as long as we're within a certain distance from A, the linear approximation will be close to the value of f of x. Okay, so now what about 2.1? If we wanted to find f of 2.1 and we wanted to approximate it, we would use our linear approximation, our tangent line. So what we would do is we would just write in 1/2 minus 1/4 times 2.1 minus 2, right? And so what would we get? We'd get 1/2 minus 1/4 times 0.1. Okay? And of course, this would be 1/10 of 1/4. So that would equal 1/2 minus 1/40th. And of course, we could change this to 40ths, right? So that would be the same as 20/40ths, which would then give us 19/40ths as our approximation. So that would be the linear approximation, right? Now the actual value is pretty close. So if I do 19/40ths, what do I get for 19/40ths? Let's just do the decimal. see what we get. So 19/40ths. 0.475. Okay, now what's the actual value? Well, we could just use the reciprocal, right? So that'd be 1 divided by 2.1. And it's 0.4762. So it's accurate. It's accurate to the hundredths place, right? So we don't see a difference until we get to the thousandths place. So it's off by approximately 1/1000th, which ain't bad. Okay, depends on how much accuracy we're shooting for. Okay. What else do I want to say here? So the bottom line is as long as we're close to the A value, linear approximation is a pretty good approximation. So now, but note that if you take x values that are far from 2, then obviously the accuracy goes down. Okay? So be careful of that. Okay, so now here's the main thing. In general, before I go end this video, it says, in general, the differentiation of the function f, the equation of the tangent line to the function at A, can be used to approximate f of x near when x is near A. Okay, so what we can do is, it's not equal, but it's an approximation. So what we can say is that that's the equation of the tangent line, right? This is the equation of the tangent line, but if we want to use linear approximation, what we would say is f of x, so this is the function, right? So the value of the function is approximately equal to the linear approximation given by y, which is f of a plus f prime of a times x minus a. And this is what we're going to use for our approximation. And again, for values of x that are near a. Okay? And what we do is we call the linear function, okay? And so we give this we denote this by using a capital L of x, okay? And we call this linear function the linear approximation or the tangent line approximation of f at x equals a. And the function L is also known as the linearization of f at x equals a. So let me write this down. So this is going to be called the linear approximation of f at x near a, right? So that's one way of saying it. Or x equals a, I'm sorry. In this case, x equals a. Okay. Or we can call this the tangent line approximation. Of the function at x equals a. Or we could call the linearization of f at x equals a. So now what we're going to do is we're going to do some examples and see how this works. So again, make sure you understand this, and then come back and we will do some examples. Have a good day.